All right, so I'm Eric Koch. I'm a postdoc at the Center for Astrophysics, and I'm really excited to be able to present an almost completed observational, or the project that we've almost completed the observations on, the local group L-band survey, this VLA extra large program that will provide the VLA's H1 and 1 to 2 gigahertz radio continuum legacy view of these northern local group galaxies. And so I'm giving this on behalf of a large team. A number of people are here. I'm specifically going to call out the technical contributions. A lot of work has gone in from, in particular, two people, Sumit Surbadikari, who's attending virtually. You're going to hear from him after the break, as well as Nick Pingle at Wisconsin-Madison, who's doing a lot of handling how do you actually image these really massive H1 data cubes. So we already heard a great introduction by Christine a couple talks ago. So this is the sort of hyper-resolved version of what does H1 look like in the very nearest galaxies. And so one of the biggest reasons for looking at H1 and nearby galaxies is really that we can get this massive range of spatial and spectral scales in this important tracer. So I'm going to start from what I'm going to call as the large scale, is sort of just beyond the scale of the galaxy itself. So understanding how gas is actually being added and removed from a galaxy, and that's really the important connection if we want to connect the redshift 0 atomic gas properties to galaxy evolution as a whole. So we then move into the scale of the galaxy itself. Christine talked a lot about this already with the galactic structure. And so one of the other important points about here, especially at redshift 0, is that it's the atomic gas that dominates by mass over the molecular gas in most of these galaxies. So if we want to understand the larger scale dynamics at redshift 0, we really do want to understand the atomic gas properties. And the part that I'm really going to focus on today is what do we get when we really, really resolve the H1? So down to the scales of individual star forming regions, where we can start to connect the atomic gas to the actual star formation cycle. So how does H2 form from the atomic gas, and how is it returned after feedback destroys that molecular cloud? And one of the most important points for why we're doing this type of large study in the local group is that we need sufficient surface brightness sensitivity to detect this thermal line. And so the best that we can do right now is really about 6 arc seconds with the VLA, so that's about its B configuration. And if we map that to about the size of a molecular cloud, which is about 20 parsecs, we can reach those physical scales within about a megaparsec. So this makes the local group galaxies extremely valuable for this type of study to link these range of scales. Right. So the local group L-band survey, mostly from the H1, is going to be able to trace different aspects of all of these red lines here. And so we're really trying to put together this very rich data set. The other important thing that we get out, and that's the two red components here on the baryon cycle, we also get the radio-free emission from the H2 region, telling us about the massive star formation, as well as the synchrotron emission from the supernova remnants, injecting energy back into the ISM. So what is LGLBS as a whole? This is 6 targets using all 4 configurations of the VLA. We've been observing for about 3 years. We're finally going into our last semester of observations, so most of it's already complete. And so we're looking at the 2 big galaxies in the north, M33, M31, as well as 4 north enough star-forming dwarf galaxies that the VLA can easily observe. I'll also really highlight that there's a lot of complementary science that we can do with some of the projects going on with the Australian SKA Pathfinder, in particular the gas cap survey, which is giving us the H1 across both of the Magellanic Clouds at slightly higher spatial scales. So we can do a lot of comparisons with that work as well. Right, so see, these are some of the best studied galaxies in the sky. Why are we re-observing them again with this much time of the VLA? And the reason for this is really the Jansky VLA upgrade gives us this massive flexibility with the correlator. So at the same time, we get the full 1 to 2 gigahertz radio continuum. We get that with polarization as well. And we also get a number of spectral lines, hydrogen radio recombination lines, 4 hydroxyl lines around 1.6 gigahertz. So that's mostly going to be tracing the masers, as well as the 21 centimeter line. And so the important thing for the 21 centimeter H1 line after this upgrade is we can combine a large enough bandwidth to get the full rotation curves of these galaxies. So in particular, M31 is a massive galaxy, but we can do it with really fine spectral resolution, so down to 0.4 kilometers per second. So physically what that's corresponding to is we'll be able to resolve thermal line widths of gas with temperatures down to 100 Kelvin, which is what we expect most of the cold atomic gas to be. So we get this really wide range and good handle on the H1 from the spectral perspective. So just a quick preview and some of the goals of this survey. For the radio continuum, this is our map of the star-forming starburst dwarf galaxy IC10. So our new map made by Sumit Sribatikari is what's being shown in the blue here in this composite image. So you can see some beautiful radio jets. There's also that big blue blob in the middle. This galaxy has this large kiloparsec scale non-thermal superbubble that's particularly interesting. The other thing that you're seeing is the white spots. Those are overlapping with archival H alpha. So that's where we're getting the free emission from the H2 regions. And so with this, we're looking at to try to almost complete the radio bright supernova catalogs in all of these galaxies, as well as getting this very detailed view of a optically thin tracer of all the massive star formation within these galaxies. For the H1, we're really pushing down to get the highest resolution that we can get with the current VLA. That's, as I mentioned, that's sort of about 20 parsec scales. And then we can use some of the more compact configurations to trade off, like Christine was talking about. We can trade off and get slightly lower resolution, but get much better surface brightness sensitivity. And so that's what's being shown in the red here. This galaxy has had a lot of recent feedback. So you see the H1 in these big feedback-driven shells. And so we want to understand the phases of the H1, the separation of the cold and the warm gas. Is there evidence of these cold-bound H1 clouds that would be the precursor molecular clouds, the very earliest stages of where stars are going to be forming in the next generations in these galaxies? What's needed for that molecular gas to form? And then how does that energy creating the shells that you can see in this galaxy here, how does that drive turbulence in the interstellar medium? So just as a quick preview, here is our first view of our 4 star-forming dwarf galaxies, and this is about 100 parsec scales. This is the C and D configurations with the current VLA. And so even from this small sample, there's quite a richness amongst the 4 different targets within the survey. So these are really rich data sets that we'll have a ton of fun exploring. The science highlight that I'm mostly going to show is actually going to come from some of our Pathfinder data that really motivated us to take on this much larger project. So I'm going to talk a little bit more about the properties that we're seeing in M33 and M31. And so starting more on the galactic scale, just so you get a sample of the richness of the data, I'm going to show you a rendering of the 3D spectral line data cube. So as the movie plays, I'm going to turn the cube on its side so that roughly along the y-axis, you're now seeing the velocity axis. And so as it spins around, you can see the complexity that's coming from the galactic structure in M31. You see these distinct spectral features that are corresponding to the rings or the galactic structure of M31, sorry, the spiral structure in M31. And so on the larger scales with these maps, we can really just start to disentangle what is the complex galactic structure within some of these very nearby galaxies. To get a slightly better sense of the complexity that we see on smaller scales, I'm going to instead change our view a little bit so that we visualize what do we see in some of these individual spectra. And so I'm just showing you 4 of the roughly million spectra that are in this data set. And what we see is a vast range of complexity. None of these spectra look alike in this particular sample. Right? And so in the absolute simplest case here, if we have this warm H1, it's optically thin. The line profile is going to be broadened by a combination of thermal and turbulent motions. That would just give you this sort of simple Gaussian profile. And we don't see that anywhere. We see this complexity of multiple components and other different features. And so the real challenge and exciting part with this data is actually figuring out, well, what does this tell us physically about the H1 medium? And so from that large scale view, we got an idea that some of this, so these really wide separated components like we see in the top spectra here, that's the galactic components. We'll see multiple structures along a line of sight. There could also be some places where we actually do just see multiple emitting volumes of H1 along different lines of sight. It's just a complex medium. What we'd really like to be able to do, especially on those molecular cloud scales, is to better understand the H1 phases, the cold and the warm gas. And if we can separate those out, that'll give us a much better handle on the turbulent properties within the atomic ISM. And so focusing a little bit on the phase, the way that we typically do this in the Milky Way is we pair two different properties of the H1. So we get pairs of spectra that look like this. In the bottom spectrum, this is absorption against a bright background continuum source. That's mostly telling you about the more opaque components, the cold gas. When we look in the emission, it's some mixture of the warm and cold gas, and a mixture of optically thin, the warm, and optically thick, the cold. And so by combining these two, you can then calculate almost directly what is the fraction of warm and what is the fraction of cold gas. And we can do this pretty effectively in the Milky Way. You essentially look at almost any line of sight, and you will get H1 typically. And so you can just choose your bright background continuum sources. But as we move to an external source, there's just a limited number of sources that are bright enough to do this. So for example, for M31 and M33, we have about 10 to 20 solid sources where we can do this currently. And while LGLBS will be able to do this with a few dozen more, we're really limited on the number of lines of sight that we can do this with. So ideally, we'd like to do this with emission alone. The reason why we care so much about this is that we expect the properties of these phases to vary by environment, and we don't have great observational handles on this beyond our own Milky Way, and a little bit just now into the Magellanic Clouds. So I'm showing you here phase diagrams that are predicted for the H1. The top is temperature, the bottom is pressure, and it's being shown as a function of density. The curved lines that you see are the equilibrium between heating and cooling processes in the neutral ISM. And what we typically refer to as the cold and warm is that narrow range of pressures you see on the bottom, where there's multiple pressure equilibrium points. So the gas can be in two different phases at the same pressure. The important point here is that blue and that orange dash curves. That's what happens when we start to change the properties, the metallicity or the radiation field in that gas. And so there's this prediction for vast changes in the properties of the H1. Without being able to actually sample this in other galaxies, though, we don't have good constraints on these theories and these variations. But for example, if the cold gas is leading into your molecular gas and setting the star formation, this can have a significant effect on how galaxies form their stars. So one thing that we do potentially expect, though, is that the shape of the emission can be affected by the opacity if the gas is cold. So this is showing a number of lines of model spectra where the emission becomes opaque and sort of becomes this top hat-like feature. And so this was focused on in this wonderful Westerbork data set of M31, where they started to see these sort of flat top profiles. Now, one of the important aspects here is this changes pretty much all the fundamental properties that we estimate from H1. In particular, we use the integral under the spectrum to estimate a column density and therefore the mass. So if it's actually opaque and we're missing a component, that means we're underestimating the mass. But what we wanted to revisit with this higher spectral resolution that we now have access to with the VLA is whether or not these are actually overlapping Gaussian components that we can now resolve with the higher spectral resolution. So the way that we did this is you set up this model test. We compared the two different models and how well they fit the data across the two different data sets that we have for M31 and M33. And we found pretty overwhelmingly that when we do have that high enough spectral resolution, we end up finding multiple components instead of necessarily just these flat tops telling us about the opacity of the gas. So these are maps of the model preference. Increasingly, blue is a stronger preference for the multiple components rather than the top hat-like shape. And so this is really saying that, when we revisit these things, the different physical models for H1 can vary what we infer quite significantly. And the biggest difference with this data set compared to previous really is the spectral resolution. The spectral resolution really does help us determine between different models. So we took a subsample of our data, we downsampled it a little bit, and we ran the same model comparison test. And what we found is that as you downsample your data, your ability to distinguish between those models goes down more and more. So that's what's being shown in the orange. And so we're losing that very blue tail, which is a very strong model preference for the multi-component Gaussian, as we simply just downsample our data. And so this is really the beginning of the story still. We have this incredibly rich data set, We know that this isn't just a collection of Gaussians. There's a lot more that we can do to try to add more physical properties and understand the complexity of these spectra. And hopefully that will tell us, and we'll be able to better disentangle all of these different effects, the larger scale galactic structure, multiple components, as well as the opacity and the turbulent properties of the H1. So looking forward, we're able to do this with the VLA right now, largely within the local group, and maybe for a couple local volume galaxies that are particularly near. But what we'd really like to be able to do is get this very high resolution detailed view of the atomic gas across the nearby galaxy population so that we can fully sample how H1 varies and how that connects to star formation and other properties of these galaxies, how these galaxies evolve. So this is the specific star formation rate as a function of the stellar mass. That's the contours that I'm showing here for the, and on top is the green points. That is M33 and M31, right? So we have 2 points of a slightly more massive galaxy. It's a little bit hard to infer how things vary as a whole. What the SKA and ngVLA really add is the ability to do arc-second thermal line imaging. And so if we set, let's say, go to about 100 parsecs corresponding to an arc-second, that would allow us to go out to about 25 megaparsecs. And now we have about 2,000 galaxies to sample from and get this level of detail. And so it'll be difficult to get all these galaxies, but we will have the population and the ability to get a representative sample and truly connect the resolved H1 properties to and how they vary across the full nearby galaxy population. And so with that, I'll leave you with my conclusions. And I'll very briefly note that we've done a lot of quality assurance work on the VLA L-band data, including interactive plots and things like that, and I'd be very happy to discuss that with people as well. So, thank you.
Thanks a lot, Eric. Questions? Yes, Tatra.
A great talk, thank you. So actually for the Galactic H1 study, actually, we see too many details and it's really hard to decompose all the gas component. So I'm wondering if you push the angular resolution, push the sensitivity, could you face the same problem in galactic, extragalactic data?
I think so. I think we might have an advantage though, in that we can probably derive a pretty good picture of what the three-dimensional structure of the galaxy is, including some of the models that Christine was talking about. So we can also work backwards from there and provide physical constraints. But absolutely, it will be difficult. And we are, in terms of complexity, starting to see the complexity that we typically see in Galactic H1 in these other systems. That's very much true of the gas cap data of the Magellanic Clouds as well.
Toby, back there.
Yeah, thanks very much. It's really beautiful data set. And I have a related question, actually. So you have this great diversity in spectra. And I was wondering if you're able to basically turn it into like a classification problem where different spectra come from, say, different locations within the galaxy or correlate with whatever feedback or physical mechanism. That's
a great idea. And it has been quite difficult, whether or not you should trust the property of just adding, some number of Gaussians. It's really difficult to say what that would then be physically, but certainly trying to classify it or stack based on, I don't know, brightness of H alpha. Do you see signatures of neutral outflow near H2 regions and things like that? I think that's something we should definitely explore.
With your increased coverage, you'll now get radio recon lines and OH, and so you'll be able to sample different phases and make correlations. Yeah, Lister.
Hi, thanks, great talk. To get the opacities right, you need the column densities to be right. And some of these guys are quite large, extending over many primary beams. Do you have commensurately high quality new data from GBT or FAST?
Yeah, I should have added, this isn't just VLA data. The M31 data initially had data from the EBIS survey, so from Effelsberg. M33 was GBT data, but we do have GBT data existing and a high enough quality, should be high enough quality for all of our targets. So that's being added in.
We have time for one more question. Okay.
Hi, great talk. I was wondering, do you think it'd be possible to correlate specifically the level of turbulence that you observe with sources of turbulence? So either currently active supernova remnants or maybe slightly older populations of stars where you assume that supernovae went off?
Yeah, so some of these things have been tried, and we certainly need to revisit it with the more complex data. I'm actually going to defer a little bit because I think Sumit Sarbatikari's talk in just a few minutes is going to cover some of this.
Very cool, thanks.
Great. And Eric, one of the mysteries is where the OH masers are in M31. Recently, they found thermal OH, but you're going to find all those OH masers, right?
I hope so.
Good. Okay. All right, let's thank Eric and all our speakers. All right, back at